All right, complex ions. Now, this is a different lesson I'm throwing in the middle of everything. There is a worksheet there, and there's also, there's a note sheet and then a worksheet, okay? That's some complex ion reactions. Now, this is something that you need to know for equation prediction that I haven't had time to go over yet, and I just didn't know where to put it in. I thought this would be a good place. Well, something's going on with my video here. Hopefully it'll stay lined up. We'll just see what happens. Okay. Oh no, I went too far. I got it hanging in there. Okay. So what in the world are these reactions? Well, let me show you an equation first of all. In predicting reactions, you know there's single replacement, double replacement, synthesis, decomposition, combustion. Guess I went in a weird order there. But what in the world is this reaction? If you look down there at the bottom of letter A, I'm just going to go to the reaction and I'll come back and talk about what's going on. Excess sodium cyanide. Okay, a key word that you'll hear on this is excess or concentrated, or it could be this or both, excess concentrated. But what is sodium cyanide? Well, sodium Na, cyanide Cn, -1, +1. Okay, excess sodium cyanide is added. Now I didn't tell if it was a solution or not, but we'll assume it's excess concentrated, and that would mean it's a solution. Well, no, or it could be a solid as well, but we'll start off with the aqueous. Excess sodium cyanide is added to a solution of silver nitrate. Now, silver nitrate is AgNO3. You should know that. Now, at first glance, you might think, oh, it looks like it's going to be a single replacement reaction. That's what you might think at first. But since the word excess was in there, something else happens. It turns out that, well, let me start off with a little bit. If it wasn't excess, yes, you would get AgCN. You would get a solid sodium cyanide. If it were not excess, you'd get this. But here's a really cool thing. If you continue to add more and more sodium cyanide to this, a solid, of course, would be a precipitate. It would come out as a solid. These two would be both dissolved, like clear water, and it would get cloudy white over here. Okay, that would be a white solid. But if you continue to add more and more and more sodium cyanide, it will disappear, and it will be clear, colorless, because you would form what's called a complex ion. Some ionic compounds, if you overload them with a lot more chemical, they will actually find a way to fit it on there, and they will fit them on the solids will fit the cyanides all around it, and then they actually become soluble in water as well. This thing keeps on moving. Well, actually, if you remember when we talked about hydrate, formulas of a hydrate, water molecules surround a compound to dissolve it. Well, also in a solid compound that's a hydrate, water molecules surround the solid. They're in the structure, even though it is still solid. So it's a similar thing to that. In fact, when water dissolves something, that is a complex ion. But anyway, so what does it produce? Complex ion. For a complex ion, what you do is this. When you realize it's a complex ion, don't treat it like other problems. In fact, sometimes I'll just go underneath it and I'll say, okay, who's going to make the complex ion? It's pretty much always a transition metal. It will not be like a group 1 metal, but a transition metal. Now, if you see a metal in the reaction that is not a transition metal, if it's the only metal present, then it will have to be that metal. But usually it's a transition. And what I mean by that is it's a metal that usually is in the center. But it could also be aluminum. It could be other metals too. But those are the ones that we normally hear about. Okay, so you put the metal and you put its charge as well to keep an eye. And then you put next to that what's called the ligand. So you put the transition metal plus you put the ligand. The ligand is the attachment. What is going to attach itself to silver in an excess form? It'll be the cyanide. So the good news is, it would normally be cyanide, but you're going to attach excess cyanides. Now, how many excess cyanides should you add? Well, the rule of thumb is you double the charge. If I double plus 1, that's going to be plus 2. I'm going to put 2 cyanides. Now, don't forget, each cyanide is -1. That did not change. But since I have 2 cyanides attached to silver, what's going to happen is think about what the charge will be. -1, -1, and +1. It's a -1 charge. The overall ion is -1. Now, what you can do is, in fact, it's on the paper here, and you'll see right there, AgCN2 is called dicyanosilver. Dicyano, is that really the name of it? Dicyanosilver or silveride. Well, the good news is you do not have to name these. AP is not going to require you to name them. However, they could give you the name and they might ask you to draw it. So if they said dicyanosilver, 2-cyanide silver, that you attach that to there. Okay, now I'm not finished with the equation yet. Let's make it now in the net ionic equation form. So I like to do it this way because I don't want to confuse myself that it's going to be a single replacement or double replacement. So NaCN, AgNO3. I know that I'm going to get AgCN2 with a negative. And will there be anything left over? Well, the silver cyanide, the sodium and the nitrate will be left over. And you probably can already tell that sodium and nitrate, because it's going to be in a solution, they're both going to be aqueous. So I'll just go on and put them separate. Here, all right, I told you that we decided that we'll let that be aqueous on this problem. That is aqueous, it's a solution. These are all complex ions, always dissolve. And a lot of them have really neat colors. Okay, that will be, of course, aqueous. That will be aqueous as well. I mean, that dissolved. The only reason I write the aqueous, you don't have to write aqueous. It's just so that I remember that I need to split that up. Sodium, cyanide, silver, nitrate, silver, cyanide complex, and then sodium nitrate. So anything you see twice unchanged gets canceled. Nitrates are gone. Sodium's gone. And there is your final reaction. Oh my goodness, what's going on here? Oh no. Okay, I'll try to, sorry about that. How, my goodness, what is going on? I am really sorry, but hey, that makes it more exciting, doesn't it? Okay, so cyanide adds to silver ion to make AgCN2, all the -1 charge on the entire thing. Okay, there it is. And of course, if I want to balance it, because they allow you to balance them, you put a 2 there, and that's all. There is your net ionic for forming that complex ion. Okay, that is how it works in a complex ion. Now, there's a lot more to this story, but I'll just tell you, if this had been a solid, let's just take a side note, if that had been a solid, well, then that would be a solid, and that would mean that NaCN would not split up right here. It would be NaCN plus that would split up, and that here now at this point it would be split up because it would what would you call it? It would join the cyanides would join there, but the sodiums would not be crossed out because they were changed. Here it's sodium cyanide, here it's sodium ion. So that's how it would look if it were a solid. Make sure I got that right. It would be sodium cyanide plus silver ion, gives you silver cyanide plus sodium ion. Looks kind of like and the nitrates would still be canceled out. So I could just take them away. But that's what it would look like if that had been a solid. Just for a little side note in case you wanted to know. So with complex ions, just to predict the reaction, that's one thing. But then to know whether or not, what do you cancel out? That's another thing that AP likes to do. To see, are they paying attention? Did we add? We could have added excess solid sodium cyanide to a silver nitrate solution, and that would give you what I just showed you. So you get the same product, but it's just different things get canceled out. Okay, so here now I'll go through the notes and show you what are the possible chemicals that can cause a complex ion. They're limited, thank goodness for you. And here they are. The main ones are, water is one of them, but you don't see that a whole lot. I'll talk about that in a minute. Aqua. NH3 is a really important one. Ammonia. Okay? It's called amine is the name for when you put it around with two M's. You might remember amine coming up like amino and amine group in organic, but AMM. Hydroxide can do it, hydroxo. And then all the halogens, chlorine, fluorine, I think bromine and iodine could also do it. Cyanide, CN, and then SCN, thiocyanate, thiocyano and cyano. And there it is. So those are the main ones they use. They have put H2O before, I believe. H2O, NH3, OH, Cl. These are the main ones. But I'd say bromide and iodide could also do it. There they are. Okay, but the key, you don't have to worry so much because when it says excess concentrated, you know that there's going to be a complex ion. All right. Okay. What is the coordination number? I forgot to tell you that. AgCN2. The coordination number is, for this one, the coordination number equals 2. And it means how many ligands are attached. Okay? A coordination compound. Okay, this has happened before on AP, but is rare. But now, remember, this dissolves in water. So, the dicyanosilver is a -1 charge. What if I took a positive ion like potassium and I put AgCN2, all that's -1, all that's +1. And sometimes what they'll even do is they'll put brackets around this whole thing. That makes it a little bit easier, right? So that way, this is all -1, that's +1. You don't really need brackets for this particular one, but it kind of helps it out. Or what if I had aluminum with, what would you call that, dicyanosilveride or something like that? There's a 2 there, and there'd be a 3 there. So you could have a compound. You could have a solid of potassium with this silver, because it's overall it's -1. So I think one of those with potassium. You wouldn't have to have the brackets. Okay, so the part 2, here it is. Got video cut off problem. I was just showing you that you could have 1 in one of these, or you could have 3 -1s. This entire compound is -1. So I could join it on to a potassium +1, and you wouldn't need to have these brackets. Or you could join on to aluminum +3 and 3 of these complex ions. And in a solid form, you could have that exist. Now I don't know if every coordination compound can do that, but I'm just telling you, if they named a compound that way, I guess aluminum dicyanosilveride ion, some goofy thing like that. I wouldn't worry too much about seeing that. There are names on that worksheet to show you how you can name these. And in your textbook, it will show you how to name complex ions as well. It's not a bad idea to kind of look at them, just in case that ever popped up. But just know that they have never asked you to name one, but a few times they've given you the names, and they usually only give you the ones that are right here in that list. Okay, coordination number at the beginning of the notes. That tells you how many ligands are attached to the transition metal, and there's 2 in this case. The coordination number will be 2 because 2 cyanides are on it. Now, an interesting thing about that, you can also tell, they ask you sometimes, what is the geometry of that ion? And since there's 2 things attached, guess what? 1 and 1, that'd be linear. Because your silver ion would be here, and then you'd have a cyanide on one side, okay, and then a cyanide on the other side. So, I mean, you'd actually draw like a Lewis dot diagram for it, but just imagine that just to be like this attached to those, and they would be linear, they'd stay as far apart as possible. Wow, for my video to cut off and for this thing to be moving around is some kind of fun adventure for me here. But hey, it keeps me awake. All right, now, what are some other possibilities? I wrote on here, they're cationic and anionic complexes. Well, anyway, that's just different names. Oh, some really goofy long names on here. I wouldn't even worry about it. You don't have to worry about trying to learn these or name these things. Wow, there I go again. it's hard to explain, but my stand is like inclined, and normally I have it straight and flat. I'm gonna have to fix that, but it's too late now. I've already started the video, so all right. Let me just try to show you a few more. This is not a long thing. It just takes a little bit of practice. Like letter A, I did that one for sodium cyanide. Letter B says, okay, here's a really good one. B1, or it says B1. Excess concentrated ammonia solution is added to nickel 2 sulfate. Excess concentrated ammonia. So when they say excess concentrated ammonia, ammonia is NH3, nickel 2 sulfate is NiSO4. Nickel 2 sulfate solution. Let's make it solution, okay? Those words should have been added. Excess concentrated ammonia will always have to be a solution. So they don't have to say the word solution. But excess concentrated ammonia is added to nickel 2 sulfate solution. All right. So can you tell now? Okay, we know it's going to be a complex ion. Who's going to be the central metal? Obviously, nickel. What is the charge of nickel in this one? It is positive 2. Negative 2, positive 2. So we put a positive 2 here. Now, how many ammonias should you attach? Since it's positive 2, double that number, you get positive 4, and I'll put 4 ammonias on it. Attached to the nickel. Now, guess what? Ammonia's charge is 0. So, that means all I'm going to do is just put that plus 2 over the entire thing. So this entire ion. You could put a bracket around the whole thing. You don't really need to do that because we would understand that to be positive 2. But sometimes you might see it, certainly if you make a compound, if you join this with something else. But that's good enough. Tetraammonia, or tetraamine, A-M-M-I-N-E, tetraamine nickel 2 ion. Tetraamine, amine, it's on there, the top there. Tetraamine nickel 2 ion is what you form. Okay, now how would you write the net ionic? Looks like it is slipping a little bit here, and I'll try to fix it. For the net ionic, let's just show, we said ammonia was, this was aqueous, but it does not break up into anything. The nickel sulfate will dissociate because it was aqueous, and that will give me my ion. See, I like to, I don't want to start off by doing a double replacement because it might just mix me up, even with the whole thing. This is forcing me to think, what am I going to produce? Okay, the nickel ammonia complex. And then I'm going to have left over, okay, the nickel is in there. The sulfate, we don't see it anywhere, so it must be a spectator ion. And the ammonia went there too. So just the sulfate's the only thing. So there's your reaction. Ammonia plus nickel gives you the nickel complex. Now, of course, if you want to balance it, you put 4 ammonias join on to a nickel to give you nickel, ammonia, the 4 ammonia nickel 2 complex. What would be the geometry or shape of this one? Well, with 4 things attached, you can say tetrahedral, or you can also say square planar. But just go with tetrahedral. It might be easier to bring that one up. Now, I know I had to cut the video, but I remember I have another thing. Well, I can show you probably a couple more, and then I'll be all right. Now, these have really amazing colors, and I'm going to have to show you in class one day. But this will get you started to draw a lot of these. Let's see. Ammonia is added to nickel 2 sulfate. B2 is the same as B1. Oh, wait a minute. Ammonia or concentrated. Oh, boy. You know what? That's actually something I'll have to wait for that to another chapter to show you. Oh, and here we go again. Okay. Excess. Okay, this is an important one, though. Letter C. C is a way to reverse the reaction. And it says excess hydrochloric acid is added to a solution of tetraamine nickel 2 nitrate. Oh, boy. So here we go. Tetraamine nickel 2 nitrate. Now, all of this is positive 2, remember? But now, if it's nitrate, that means you'd have NO3 negative 1 attached to that, which means, oh boy, now I'm going to have to put this, and NO3 2. Wow. What a weird one that is. That whole thing is positive 2. That's negative 1, so you need 2 of those on it Did I do that thing right? Yeah, I think I did. Yeah, it would have to be that way. That positive, negative. Won't hurt you anyway to write that way. What will that give you? Okay, well, the HCl is going to pull off the NH3 and make ammonium, NH4. Okay, so, by the way, this was already aqueous. It was a solution, so technically that's going to be split up anyway, but I just drew it that way. So what's going to happen is, in the end, you are going to get NH4 plus. You should know that HCl and ammonia always gives you NH4. That's a reaction in itself. That will give you NH4 plus. And, of course, you'll get Cl as well. But the Cl will end up being a spectator ion, ammonium chloride. So ammonia, actually, hydrogen chloride, if this was a gas, let me do it two ways. If this were a gas and ammonia is a gas, you get ammonium chloride solid. Really cool. But if HCl is aqueous and NH3 is aqueous, you're going to get ammonium, NH4 plus, and Cl negative. They're both going to be aqueous. And of course they'll be split apart. The HCl will also be split apart for that matter in that one. But okay, we'll see it again down here. But these are two little reactions, kind of like side note. This actually involves a later chapter, acids and bases, but it's good to know that right now anyway. Those two things you might want to just write down for your little catalog. But anyway, your mental catalog of equations. So here we go. So HCl, so that's going to break up, and it's going to react with Ni, NH3. Oh boy, I'm going to have to take more space. 4 plus 2 plus nitrate. They said this was a solution, so I didn't really need to put it together. But I did put it together and say aqueous, but in my net ionic, I'm going to break them apart. And that what's going to happen is the H plus is going to take the NH3 to make NH4 plus. Then your nickel actually is now free. Yay! Now, nickel is free, and then nitrate will also just stay as it is, undissolved. So, we take away nitrate and nitrate. We don't take away the nickel. NH4, we don't take that away. Oh, the chloride. I didn't draw the chloride on this side. Chloride will be another. It had to go somewhere, and I forgot about little chloride. Okay, so there it is. So the 8, and that's plus. H plus, when I split up HCl. H plus Ni. So H plus pulls off the ligand, and it reverses it. And it makes ammonium, and then nickel is free. There is your net ionic right there. Fun stuff. Now, these have really amazing colors. Like this one I think is a blue color, but then but nickel is green. Nickel is green, but its complex is blue. And I'll show you that sometime. It's really cool. All right. There's one more thing I want to add for those really, all my straight A, hard-working, I'm going to make a 5 on the AP students. Let's just say that for some reason in this reaction, that this had been like, I don't know how it would have been, but just say that this had been like a carbonate, CO3 -2. Just pretend, if that had been a carbonate, what would be different about this reaction? Well, the nickel and the carbonate on this side would not be split up because nickel carbonate makes a solid. So you'd actually form a precipitation of nickel carbonate. So that would be a really tough one for them to throw that in there. But nitrates, they all dissolve. No big deal. And if they said it was a solution, even if they said it's it's this ammonium tetraamine nickel 2 carbonate, and that wouldn't be the formula. And they said it was aqueous. If they said it was aqueous, then you could trust it's aqueous. Okay, when you split it up. But in the very final step, when that nickel is liberated, +2, did I write the 2 on it? When that nickel is free, +2 charge, if there's a carbonate around, that's going to form a solid. So that would be another thing. That's not a real likely thing, but it could be. Okay. So it can erase or reverse that reaction. You know what? I hate to have to pause the video. Let me see what I'm looking like, because I might have to do. Yeah, I might have to come back. I can show you. There are 2 other ones I want to show you with hydroxide. Yeah, I need to at least show you two or three more of these. E, and there's one that's not even on there, so I'll have to show you. I'll show you a few more examples. Yeah, I wish I had, but I gotta do one. I don't have. I probably need about 10 more minutes, and I have to do something right now. Another online thing. So I'll have to pause it. Sorry for all this moving around craziness. I'll see. Okay, this is part 3 now. Oh, so I've just had. It's been a crazy day, and I'm sorry about this. I think at least I fixed one thing. I don't think it's going to move around after this now with the screen. Okay, so the complex ions. The main thing is you see it'll be a transition metal, and you know what things are going to be surrounding it. When they surround it, water, aqua, it's called aqua in the prefix, amine for NH3, hydroxo for OH, chloro, fluoro for chlorine, bromine is probably bromo, iodine, iodo, and then cyano for cyanide, and then SCN, thiocyano, okay? One time I saw something like thiocyanato, but it doesn't matter. They're not going to ask you to write that down. But if you saw, well, I'll show it to you in a minute. Okay, so here we go. All right, now I put some examples of the complexes on the side and how they name them on the left right there. Like if it says hexa aqua, you could cover that up and just see, are you able to write the formula of it, of each of these right here? You can try it on your own. Hexa aqua cobalt 2. Hexa aqua cobalt 2. So hexa means 6, aqua. 6 aqua is water. Hexa, aqua, cobalt, 2. They kind of name it backwards. So that's all one giant compound. Actually, this is a complex ion. Anytime something dissolves in water, that's pretty much the ion it forms. You know, we always say, let me think about this for a minute. What is the net ionic equation for dissolving copper 2 sulfate in water? So let's say you have solid copper 2 sulfate dissolving in water. If they were to ask you to do that, it has happened before, but as far as I can tell, looking through like 80, 90, 85 years of the AP exam, I think I only saw it one time, and it was fairly recent. But copper 2 sulfate dissolves in water. All you got to do for this equation is write down Cu plus 2 and SO4 negative 2. And you can put, if you want to, you can put H2O above the arrow there. But you don't even have to do that. So I wouldn't do it. You don't have to do that unless they were to ask you or tell you. And you don't even have to put S for solid or AQ, AQ. I mean, you could put solid, AQ, AQ. Okay, that's a really easy one. That's called a dissociation reaction. Dissociation reaction. I haven't made a big deal about that when we did the solubility rules, but that's also a possibility. Well, what you don't know here is that when something dissolves in water, actually water molecules are surrounding it. So what you really get, if you had to write it in terms of a complex ion, then you would write this. Copper 2 sulfate with water is going to give you, as a complex ion, copper. Now here's the thing. For H2O, when it attaches, we don't usually just put 4. We almost always put 6. And the reason is because when water molecules surround any metal ion, they pretty much can surround them on top, bottom, left, right, front, back. Think about that. 6 areas. What shape does that look like? Left, right. Well, that might be backwards to you. This side, that side, up, below you, in front of you, behind you. Octahedral. So you get this complex ion. Now, if I want to make this correct for an net ionic equation, I'd say that's the solid, that's water, that's the complex. Yeah, actually, you'd have to write down all of this for the net ionic equation because everything changed. Sulfate, here it was part of the solid, here it's not. But that's the way you draw that right there. So that hexa aqua copper 2. Hexa aqua copper 2. All right, now, so you could try and just write down these things. Okay, now this is an important one. The aluminum aqua aluminum. Oh no, that's not the one. Tetrahydroxo copper 2, diamine silver. Okay, you don't need to say silver 1 because silver can only be +1. But like on copper, you had a Roman numeral tetrahydroxo copper 2. You got to have a Roman numeral because copper can have more than one charge. There could be a copper 1, a copper 2, or rarely copper 3 probably. And then silver does not need a Roman numeral because it's always +1. Okay, I would not worry too far. You're not going to have to name them, okay? But just if you saw the name, like in the worksheet problems below. Okay, so I showed you that one about the water. Okay, here's an important one. Letter D at the bottom of the page. It says excess. No. Letter E1. E1. I don't know why I numbered it this way. And a lot of these are just the same. Some of these are just with a solid and without a solid. A drop of potassium thiocyanate. Okay, this is one. Here is one exception. Every equation always says excess concentrated, the directions. But for this one, it doesn't have to say that. It can just say a drop of potassium thiocyanate. When you hear about thiocyanate, look at what it can do. Potassium thiocyanate, a drop, is added to iron 3 hydroxide. Let's make it, we can't make it aqueous because iron 3 hydroxide is a solid. So iron 3 hydroxide, none of the hydroxides will dissolve. That has to be solid, and they would have told you that. They'll even tell you like solid or iron 3 hydroxide powder or something like that, crystal or whatever. But this one is aqueous, a drop. Having a drop tells you it had to be aqueous. Okay, well here's the weird one. Iron, yes, you can make an iron 3 thiocyanate by doubling the charge, but the most common one is actually this. Fe, and remember, iron is +3, okay? SCN is -1. The most common one, believe it or not, is just to have one SCN joined to Fe. One, a single one. And therefore, if that's +3, that's -1, your overall charge is +2. Now, I don't think you're going to ever see this on the AP exam, but sometimes they've written it as ++. That means 2 positives. Seems like an elementary way to do it or something. Elementary advanced chemistry, if there could be such a thing. But okay, FESCN that. Now you don't have to put that. I've seen people write that before. You don't have to write that though, because it's only one of them. But that helps you to remember it. It's okay though. That's the correct way. So for this net ionic, these are aqueous, and this is a solid. One thing that's really cool about this, you don't really see it till you see a lab. Remember the solubility rules. None of the hydroxides will dissolve except for the camel with straw on its back, calcium, strontium, and barium, and then any group 1 metal or ammonium. But here's iron hydroxide. That won't dissolve in water. But what's amazing is when you add this chemical, which looks like water, salt water, it's a colorless. When you add it to this dissolves. So forming a complex ion makes a solid aqueous. So it dissolves into this. This is aqueous. And another really cool thing is that this is blood red. Blood red. It is like the color you see in blood. You know that iron is in your hemoglobin. And when you see that, you'll know that that's why it's red. And I'm going to show you these at some point. I'll show you in a class or video or Zoom or something. I got to do it. Got to let you see these colors. Okay. What else is happening here? So FeSCN. Now the potassium and the hydroxide will be left over. Now the potassium is going to be what do you call it? Don't forget SCN will become negative. -1 there. Okay, not become, but it was -1. I left off the -1 there. So SCN negative, FeOH3, that's a solid, give you FeSCN +2, and then you get OH negative, and that will stay there because it has changed from a solid to now being aqueous. So that's your net ionic. You're allowed to write it that way. You don't have to, but a lot of times they'll say on the AP, write it your final answer in the box. And if they say to balance it, the only thing you have to do here is just put a 3 right here. 3 OHs, because you got 3 OHs there, 3 OHs there, 1 iron, 1 iron. Okay, but they'll have you write in the box. But I'm just going to save time because I've been going on for a while with this. I'm trying to get it nearly done. I'm sorry. Yeah, this video is working better with the not moving around so much. All right, and then what was the other one I want to tell you about? Water, thiocyanate. Oh, there was something else I want to tell you about. Oh, the aluminum hydroxide. There's also another weird ion, and I'll have to show you more of this later, but you know what? I think there's one. I know there's one on the well, I'll just make it up. There's gonna be one on your homework. Okay, so let's just say that excess concentrated sodium hydroxide added to AlCl3 solution. That's not the way the questions are written, but I'll give you the formulas. So you have sodium hydroxide. It's aqueous. We know that because, well, let me see. I do this a lot. I'm thinking my shortcut way, but NaOH is aqueous. You want to think about that. Aluminum chloride is also aqueous. So you don't have to write this step down, but I like to just know that when I write my net ionic. The main thing is what's going to be formed. Okay, what do you think metal is going to be between sodium or aluminum? I think I told you, well, pretty much never group 1, so it will have to be aluminum. And now, here's another weird thing about it. Hydroxide will surround it. I believe there is, if you double aluminum plus 3, so if I put 6 of these, I think there is an ion with 6. But again, the most common one is actually this. You have 4 hydroxides. So if that's -1, you have 4 of them, and +3, you get -1. So it's called tetrahydroxylaluminate ion. It's the more common one. Now, if you put a 6 and it'll be -3, you'll get credit for that. But you know what? FeSCN plus 2, that's a common ion, and this one is too. Those are the 2 exceptions that I really that are most notable that I know about. So now for this one, what you're going to get is sodium plus OH negative, because those are aqueous, they're going to dissociate. Aluminum plus 3 Cl negative. Okay, now you get the ion, and then what's going to be left over? The sodium, nothing happened to it. There's nothing here that's going to precipitate. NaCl is not going to precipitate. Na plus, Cl minus, and so the Cl and the Na go away. So it's going to be aluminum. So if you want to write the balanced one for this one, it's less writing, so than some of these are. Gives you AlOH for negative. Now, there's one more thing I could show and just throw in real quick. I don't think I put one like this on the paper because it turns out that these can also act as acids and bases. So you can imagine I could reverse it by adding an acid to this, and it would make sense. So what about if I added HCl plus tetrahydroxylaluminate ion? Watch, I'm just making this up. But one day, and maybe this year, this could be on the AP. I mean, one time I did predict one. I was doing an equation review like right before the AP, and one that I gave in my review in class, it was exactly on the next. You guys, I am not believing this video. I mean, if I'm going to keep any of these for the future, this one is probably one of the messiest ones. 4 parts for a fairly short video, I think. This is a bonus one, I guess, anyway, but prediction. One year I was saying before it got cut off that I was doing a review of equations before the AP exam, and I mean, there's one I just picked up. How about this out of random? And it was on the AP that year. It was like the next week. It was on, or next day, or couple of days later. I had no way to know it. It was amazing, and so sometimes there's a little bit of review. Okay, well here it is. What if I added hydrochloric acid to this tetrahydroxylaluminate? Now, if you really wanted to get technical, you could add this onto something else, like a solid. Like it could make a solid potassium aluminum hydroxylaluminate. But anyway, we're not going to do that. Okay, but let's just say, what if I add that on there? Well, the H plus can pull off the OHs. That's what's going to happen there, like an acid-base reaction. So, you're going to form this. Well, you're just going to form water, H2O. So H plus pulls off the OHs and makes water. Then aluminum is now left alone, unbothered. And now the chloride is going to be there. You don't have to worry about them, these two precipitating. Okay? H plus, Cl minus. This one would have to be left together. Now, how might they add that? They could be added to a solution containing tetrahydroxyaluminate ion. They could put that. Or they could give you the compound, like I told you, a solid compound of potassium, aluminum, potassium tetrahydroxyaluminate. I really doubt that. That's like major, like a 5 on the AP if you get that one right. Like few people would get that right. But this one, a good number could get it right. If you add acid to this complex ion, it pulls off the OH to make water. Now the aluminum is now freed, and then the chlorides, of course, were just your spectator ions. So that would be your equation there. What I need to do, put a 4 here, and a 4 there. 4H, 4H, 4 and 4, and 1 aluminum. Yeah, okay. And anyway, that is all. That is all. So work on the worksheet attached. Try and do all of those equations and just practice them, and know that this can now pop up on the Monday quizzes. And another thing I want to tell you about this is, especially, I'd say maybe in the past 10 years, if you go back past 10 years, you'll see that this is probably on more often than not. So maybe like anywhere from like 3 or 4 of the, maybe 3 to 5 of them, even 3 or 5 of the past 10 years have had these on there. They're pretty common. They like this stuff. And the type where you add an acid to pull off hydroxide to make water, or add acid to ammonia to make NH4+, that's pretty rare, really rare, but it has happened before. Okay, so that's all, and complex ions.